Okay, so let's jump into the description. That's all we're going to do here. Okay, describes the practice project. So it's going to supplement, like I said, the handout, the PDF handout that you guys have already on our course site. I tried to go a little bit more in depth about what an evolutionary algorithm is, okay, because that's the part that's completely new to you. And actually, I got question from a student. I don't remember if it was by email or on one of the sections forum. I got question in the lines of, what is this? Okay, what is an evolutionary algorithm? But more importantly, why should I care? And that's actually a legitimate question, okay? But let me explain something about this. When you do, and by the way, that student brought up the point, that normally in programming classes, we do things like palindromes and stuff like that, So why suddenly are we doing something completely esoteric like this, okay? Well, the difference is that when you're talking about basic programming classes, okay, fundamentals, then generally you learn, low-level techniques. So you can practice on very small projects, okay? The problem with object-oriented programming is that OOP is an answer to one problem. How do I develop large-scale software? Okay, there are other aspects of OOP that people that actually do research in object-oriented programming would be more qualified to tell you about. But for most of the programmers, we deal with OOP technique. We learn them because they allow us to do pretty much abstraction, encapsulation, right? They allow us to break down the work in a team, in a potentially large team of programmers. Everybody has those contracts, those API, you are going to write this class. This is what it's going to do. I don't care how you implement it, but I can use it. Okay, that's one of the keystones of object-oriented programming. Well, guess what? If your programs are 5 lines in size, you never get actually to do object-oriented programming. I tried to keep my examples in the slides during the lecture simple, because I don't want to overburden you with exactly what we're going to deal with in this presentation, which is domain-specific knowledge. Okay, I don't want to have to make a slideshow on accounting because we have an accounting example. I don't want to have to make a slideshow on the stock market because we have some classes to implement that do something with data from the stock market. Okay, but this is actually the reason for OOP technique to exist. So at some point, when you learn a certain level of techniques in object-oriented programming, you are going to have to apply them to something a little bit more realistic. Okay. And don't be frightened, because as far as realistic goes, this practice project is pretty tame. Okay, it's not going to be like 5 sessions for you to get briefed up on the application domain so that you can only start implementing things. No, before the end of the session, we'll be done with the overview. You guys will have a good understanding of what's going on here. Another good question that was in that student communication was also, what do you mean by design? You give us an algorithm that we have never seen before, an evolutionary algorithm, okay? And then you talk about you guys are going to have to design it, okay? No. We are not doing algorithm design. This is not an algorithm, design or analysis class, okay? I'm giving you actually an algorithm that is already pretty much well sketched out. There are a few variants that you could do here or there. That's okay. But the algorithm itself, I don't expect you to improve it. When I could talk about design, I talk about design as it relates to this class. This is an object-oriented programming class. So I want you to use the object-oriented programming techniques that we discuss in the lecture to implement this algorithm. Okay? So the algorithm is there. It's not going to change much, okay? But you are going to try to find the best way to implement it using an OOP design, okay? An object-oriented design, actually. So with this preamble out of the way, let's jump right in, okay? And let's take a look at what we have to say about this practice project. So let's go over the learning outcomes. So the first goal, goals, both goals and learning outcome. So the first goal of the project is to implement a basic evolutionary algorithm. So you have been hired pretty much to deliver that to your client. That's a concrete objective. But this is actually a course, so this is a learning experience. So we have other things that we want to kind of thread in. There's a reason for which you have to deliver this. The first one, as I mentioned, is leveraging the object-oriented programming techniques we studied. This is not graded, by the way, right? So I'm going to come back on that in the next slide. But the idea is you need to go wild. Okay? If you ever wanted to have like 5 abstract class inheriting from one another, go nuts. Try it. Okay? You cannot go wrong. You cannot lose point. All you're going to do, and you're going to see how exactly, you're going to be able to exchange information with me, with the TA, with your classmates. Okay? You're going to be able to kind of brainstorm with others, including students and instructors. Okay? And you are going to come to the realization why some designs are better than others. And more importantly, you are going to get a lot of practice implementing and using those techniques that we talked about. Okay? So that's really the goal here. And that's pretty much what this point is saying, so I'm going to pass over it. Okay? You really need to, the key word here is as many. Okay? You really need to get to use this as an excuse to practice as many OOP techniques we discuss as possible. And you will have to wipe it and restart it. All of this is part of the practice, okay? So don't time yourself, don't put yourself in a framework where you say, I spent already 10 hours on implementing something, I restarted from scratch 5 times, I'm wasting my time. No, that's exactly the opposite. That's what you are expected to do to play with those technologies, okay? So more concretely, a few rules about how we are going to work on this project, okay? The one thing I ask of you, and I would say that this is especially true at the beginning, and then we are going to relax that rule, okay? But I want you to keep the implementation to yourself. It's not graded, so really I'm not afraid of you guys cheating, right? What I want to do with this, what I want to achieve is, it's tempting, you know, to go on the forum and say, hey, this is how I implemented this basic evolutionary algorithm. And for you, it's a good thing because you expose your code, you get feedback from others, and you can still do that with me and the TA. Come, show us your code during the office hour, during the online TA session, and we'll comment on it, we'll help you. But when you talk to classmates, when you work together, and I really encourage you to work in study groups too. But if you post, for example, on the forums, at least for the beginning, try to talk about design in general. Like say, for example, well, I was thinking about using an abstract class, candidate solution, and then subclass it with this and this. Talk like this, because this is going to allow you to really share your ideas about design level before you go into the gory details of the code, okay? And it's going to also prevent some of you that maybe are like a little stuck, they don't know where to start. It's going to prevent those students from just looking at some code on the forum, cut and pasting it and saying, well, I can read the code, so I'm in good shape. Now, if you are really stuck, you don't know where to start, that's okay. That's what this assignment is for. It should raise a red flag. That means come see me during office hour, come see the TA during online session, that's all. And we'll get you started, we'll help you, jumpstart that first step that is arguably the most difficult. But if you just, look at somebody else's code and say, well, now I know what he has been doing, well, yeah, sure, you can read code. I mean, at your level, you have no problem reading code. But that's not the same. So that's the first thing. And the second thing, and like I said, as soon as we are done with those first experimentation on design, I don't have a problem with you sharing code, but you need to get started first. The second thing is you can discuss freely anything related to design, and you're encouraged to do so on the forums. Why the forums? If you are shy, you don't like the forums, that's okay. Work together, make study groups, connect by email. I don't care, it's not graded, okay? But the forums have another example, is that you open the door for anybody in the class to jump in with their own idea, with their own design, with their own perspective. And that's what's going to really allow you to widen your horizon in terms of object-oriented design, okay? Somebody is going to hit you left field with, their 5 abstract class inheriting from one another. You're going to laugh, and then you're going to say, well, you know what? Maybe they went too far, but I could use 2 abstract class inheriting from one another. This kind of thinking process, okay? So take everything with a grain of salt. The point is not that one guy or girl is going to be right and then everybody copies it. That's pointless. No learning. But exchange information, talk to one another. If we can get to the point where you guys are comfortable having this kind of learning community going on in the forum, without being shy about good and bad ideas, then that's good. I mean, we are like operating at full speed here, okay? Otherwise, everything else is just trying to mitigate the absence for that kind of interaction. Don't hesitate to go against consensus, be rebels. Okay, like even if everybody agreed that in this case we should have a class, I don't know, a population, like my personal implementation, I'll tell you I have a class population and I put some things in it, and I'll tell you what I put in the slide as a starting point. But why would you just follow blindly? If you have a good feeling about organizing things differently, the goal is to make your implementation as flexible as possible. Okay. Over time, I'm going to ask you to implement variants. We are going to add on the requirement, okay, to have this project. And when those new requirements come from, this is when it's going to be pass or crash, right? Your implementation will ever be able to handle, that new change, that new requirement, because it's really flexible, or you're going to scratch your head, wipe everything and say, okay, I should have used like 5 abstract classes after all, okay? That kind of stuff. So you may think that this doesn't happen in real project. Not true, okay? Those of you who took even like an introductory software engineering course know that there are different models of software engineering adapted to different types of requirements. For example, if you work for DARPA, they love to have to spend, 6 months, a year, 6 years, 10 years, I don't know, designing, making like huge binder of design documents. And then once the design documents are done, it's magic. You pass them to the coders like start working, and then the testers, and then at the end you look at what you obtain, and the client goes like, well, that's what I needed like 5 years ago. But time changes, and you need to scratch this, okay? But these are big projects, okay? And in software engineering, there's no such thing as too big to fail, okay? But this is like the traditional, software engineering that started actually the field of software engineering, waterfall model, stuff like that. And then there are all sorts of approaches that have been emerging, over the last 2 decades, I would say. Like, for example, you might have heard of agile project management, Scrum methodology, extreme programming, all of those keywords, they're actually much more than buzzwords. The first time I heard extreme programming, I was like, I don't want like energy drinks, in IV or stuff like that. But the bottom line is that sometimes, we use a lot of buzzword in our field, but those techniques are actually worth your time if you want to look into them. And one of the things that they bring to the table is sometimes you have projects where the requirements change a lot and often, okay? Typically, just take a personal example, as a researcher, I never had very much use for the waterfall model. I learned it as a student, and then as soon as I started developing code for my research, I forgot everything I learned about waterfall. Just because it's not a bad tool, it's just not the right tool for a project where every week, your PhD advisor comes, or you discover a new paper that you downloaded, and you have to change everything. So it's way too, volatile, okay, as an environment. And actually, it's not just proper to research. Companies that do research and development, same thing, you have to adapt to market. Why are you going to continue working for an entire year on a feature to develop, for example, a mobile website where, for example, there is a new framework that emerged that allows you to deploy, your mobile app on all the platform, and it has this and this and this, advantage. You can access the hardware, etc. So don't let the whole principle of design, then implement, then test, trap you into a momentum where your company is going to keep working hard on developing a product that would have been good on last year's market. So this is why agile methodology have a niche where they are really useful. And when you do agile methodology, it's not unusual, to wipe clean the slate. It's not unusual to have requirements that change a lot. And that's where also object-oriented design and programming shine, is that you can write code that is generic enough, okay, to accommodate a wide range of potential changes. So sometimes you have an idea, you have a brainstorming meeting, and you have an idea that maybe in the future you'll need, for example, to have an evolutionary algorithm that doesn't only work on bits, vectors of bits, but works also on vectors of integers. Well, if you have this idea in mind, it's going to affect your design, right? You're going to make it flexible that way. But sometimes you're just surprised, okay? You still need to be able to adapt the tools that we learn about in this class to pretty much adapt your code, okay? So that's the background. Now, let's talk about like logistic. Is this practice project mandatory? Yes, it is mandatory. Is it graded? No. So please do not, put your head on the side, like my dog does sometimes, like, oh, what do you mean? No, you should be past that, okay? The problem is that if I grade this, I cannot help you as much as I want. If I grade this practice project and one of you comes and asks me a ton of questions and really needs my help and I need to start the design for them, etc., if I do that with anything graded, it's unfair. It's unfair for everybody else who had problem but spent maybe 20 hours to get started because they really wanted to do it themselves, right? So as soon as you put grading into the equation, then suddenly you have all sorts of policies. I cannot let you work with one another because that would be cheating. I cannot help one of you too much because that would be unfair, and so on and so forth. That's why I'm not grading this project. But do not confuse grades and feedback, okay? You do not get a grade on that project, but it's not optional. You need to practice with it, and you will get feedback on everything that's right and that's wrong. All it will take is for you to actually, contact me. Come to my office hour, come to the TA online office hour, book an online office hour time with me, exchange IDs on forums with our classmates, because I'm monitoring those forums, okay? Generally, I try to monitor the forum at least one time every day. So that means that if I see something that I can comment on, that I can add something to, I will be more than happy to jump in, okay? The forums are not a way to say, teach yourself, and I'm out of here, I'm in vacation. No, it's a way to say, bring to each other all of your problems so that I can address them for the benefit of the entire class, okay? So that's pretty much the idea, the philosophy behind this project, okay? And again, at your level, I'm pretty confident that a vast majority of you understand the difference between, the grade and the feedback. You can have feedback without a grade, okay? And sadly enough, you can get grades sometimes without proper feedback, okay? So the grade doesn't really help you improve. So make sure you have this distinction there. Another word of warning, again, about this mandatory yes, graded none. I know that some of you, maybe the most pragmatically minded, are going to say, well, I have other projects I need to deliver in other classes. So if this is not graded, yes, I'm going to work on it. And then by week 2, you're like, I don't have time to work on it. We're all like that. We're all pressed by time, and we end up prioritizing based on what's on fire, okay? If my desk is on fire, I will move to the next room. If it's not on fire, I'll just stay here and work, and ignore whatever deadline. So we are all in that situation. So I really want to impart on you the importance of those practice projects, okay? Pragmatically, again, to talk the language that the most pragmatic of you are going to be most receptive to, that means that in those practice projects, we are going to do some side things. Like, for example, in this one, in the first step, I want you to use property files. Well, this is not a course about using property files in Java. You guys are past that level. You can go to the documentation, see how to use property file, and then if you need help, you come again to the TA and myself for help. Okay? The TA is going to be really available, really focused on helping you through those practice projects. Okay? So the bottom line is that if we use something like that in the practice project, because it's mandatory, I assume that everybody knows how to do that and was able to do it, or if you have problem, that you came and sought the help, okay, to be able to do it. So by the time the exam comes, I'm going to assume that you have no problem with property files, okay? Again, as a way to reinforce that this is not optional. So keep that in mind, okay? An exam question can very well be about, well, we're going to change something in our practice project. And then if you find yourself opening your exam, you have 1 hour and 15 minutes to do it, or 1 hour, and you see the first question is, given the code that you developed in the practice project, that's like a nightmare scenario, right? So don't put yourself in that situation. Work on that project, get something to work, get all the help you need. Not graded. We'll help you, until you're sick of us helping you. No problem. And then another thing that is really important, as we cover every topic, we are going to build on that initial project, okay? So one other thing I'm going to do is I'm going to change a little bit the semester, the order of things, and the next topic we are going to cover is metaprogramming, okay? Instead of the original plan that was in the syllabus. The reason for that is that We have already an extension for metaprogramming that fits very nicely with this practice project. It's going to allow you, as we discover new technique, to see how they can apply to the same project. So again, to go back to that initial concern about this is new to me, you know, evolutionary algorithm, etc. Yes, it's new, but you learn it one time and then you're done for the whole semester, okay? So now let's go into the application domain specific knowledge. Okay, that client came to you, say, I want an evolutionary algorithm. You said, sure, no problem. What's an evolutionary algorithm already? So let's cover that now. The field that we are going to touch with this project is called black box optimization. Okay, so optimization means we try to find a solution to a problem, and we want it to be as good as we can. We want it to be the best, actually, possible. So it could be designing wings for an airplane. It could be all sorts of very complicated stuff. We are going to do stuff that is very simple. But whether you use a trivial example like the one we use here, or something complicated like optimizing an engineering design, the principle of black box optimization is the same. You always have something called a fitness function, or objective function, or quality function. That fitness function takes something that is called a candidate solution, okay, and then returns a number. And that number, well, depending on the optimization problem, the higher the number, the better the solution, or the lower the number, the better the solution. For example, if the evaluation is based on cost, okay? You want to lower the cost, you want to maximize the throughput of a device or something like that, okay? So that is a given. This is given to you as a black box and the name, okay? What does it mean, black box? It means that you don't know anything about that function. You have no clue. You have a method, you call that method, you give it a possible solution to the problem, it tells you how good it is. That's it. That's the beginning and end of your interaction. Now, those candidate solutions, in our case, we are going to start by assuming that there are always things that we can encode with a fixed size vector of bits. Okay, and that's it. So I'll tell you, for example, okay, this problem we work on is 10-bit long. We have 10 bits, 10 binary digits, okay, and that's all the possible binary digits, binary numbers with 10 digits are the space of all possible solutions to the problem. So it's kind of abstract, right? But that's why, you know, we talk about black box optimization in general. That could work with all sorts of problems, okay? So now, if we know the definition, if we knew the definition of f, like mathematically, okay, it told us, for example, f takes the first bit, elevates it to power 23, multiply it by the second bit, etc. Then we could use calculus. Okay, calculus, you have, if f is derivable twice, even better, you have analytical method to find the optimum of a mathematical function. But again, black box optimization means we don't know anything about the function. For all we know, our algorithm calls the fitness function, and the fitness function takes those 10 bits, use them to configure on and off, 10 on and off switches on a device, a physical device, then let that physical device run for half an hour with measuring the heat, the production, etc., and then take all of those sensors' value and gives us a number. That could be that far-fetched, okay? Each evaluation could take half an hour on a physical device with us, you know, measuring physical phenomenon to determine the fitness. So that's the mindset you have to be in. So in that case, I don't have any formulation. Finding a mathematical formulation of what's happening in that device is actually another totally different problem. But what I'm trying to get at here is that I can still optimize things even though I don't have a full formulation. So if n is small, again, like for example 10 bits, it doesn't take long even on a phone to enumerate all possible, you know, vectors of 10 bits. So that would not be a problem worth optimizing. But we assume that the techniques we define on 10 bits are going to be the same techniques we are going to use when we have like 4,000 bits or something like that, okay? So let's take an example of black box combinatorial optimization problem. And I'm not going to go over the definition of combinatorial. It's just a type of optimization problem, okay? So this is called the knapsack problem. Those of you who took an algorithm course are probably very familiar with it. Here's the issue. We have a book bag here, okay? We have a bunch of objects. So for the sake of example, we have only a few, but you could have like thousands. Each of them has a weight. Like for example, this one is 1.3 kilogram. And the knapsack itself has actually a weight limit. You cannot shove more than, let's say, 7 kilograms worth of object in it. So you want to pack those objects, as many objects as you can, in the knapsack. But in addition to their weight, they have a second characteristic, which is, represented here by those little hearts, their value. Okay, so it can be like monetary value for this ancient clock. It could be like affective value for this rabbit that's your pet since you were a child. I don't care. But the bottom line is that each object has a weight. So not all objects can fit in the knapsack. And each object has a value. So you want to fit as many objects as you can in the bag and maximize the value you get out of it. So it's called a combinatorial optimization problem because it's discrete, right? For each object, you can have a checkbox that say, yes or no, I put this object in the bag. Yes or no, it's convenient because we are using binary vectors, right? So 0 or 1. So we'll be able to apply our evolutionary algorithm to that problem without issues. For example, if I say I'm going to put everything in my bag, well, I'm busting the limit. So it's not okay. It's not a viable candidate solution. So the check, 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 okay, or 1, 1, 1, 1, that's a candidate solution. I'm considering taking all the objects as a potential solution to my optimization problem, okay? So the preference is maxed out. I just add all the arts together. The weight is messed up, so it's not a viable one. Then if I choose those guys, well, I get a preference of 3, okay? So that's not bad, and the weight is okay. So this is a viable potential solution to my problem. But look here, if I switch around and I take those objects instead, then I get more value, and I still respect the weight limit. So this solution, this candidate solution, is better than the previous one. So you could visualize this as a search space, okay, as a landscape. On the x-axis here, let's say we put all of the potential solution encoded in binary. So 0, 0, 0, 0, 4 zeros, means I take no object, and I compute the fitness of that. And then 0, 0, 0, 1, I take one object, the last one, which is a clock, and I compute the fitness. And I can have a graph like that. So again, if I have 4 bits, this graph is completely messed up, by the way. I realized that this morning. If I have 4 bits, I should have 16 different possibilities, right? So I could have a graph of 16 points, and then I just look at the graph and I know which one is the highest. That's the one I want to use, okay? But in practice, again, even though we learn on 4 bits or 10 bits, in practice, you could have thousands and thousands of bits, so that size of the search space is going to become huge. And that's what makes it interesting, is that very soon, for each time you increase by 1 the number of objects, okay, the number of bits, you actually multiply exponentially the size of the search space. So you can very easily come with an instance of the problem that would have as many possibilities as, for example, there are atoms in the universe. That number can pump up really fast, okay? So you have 1 million objects in your problem. Well, then suddenly, if you try to solve it by going through every possibility, computing its fitness every time, and then looking at the best one, you would be out of time, technically, right? It would take probably the end of eternity to finish that computation. And this is actually the essence of algorithmic complexity. That's where it's interesting. That's why instead of considering all possible solutions, we're going to use an evolutionary algorithm which allows us to not consider all solutions, but smartly navigate the search space towards the most valuable solution. So we are not going to solve the knapsack, at least at the beginning. We are going to solve a much simpler problem called the 1 max problem. Again, I want something simple. I want you to understand why those techniques are useful in real life, but I want you to implement something simple. So the 1 max problem is easy. We are going to write the function, the fitness function ourselves, okay? So we are kind of cheating. So we write the function, the fitness function, so that given a string of 10 binary digits, for example, it returns to us a fitness between 0 and 1, so normalized. And that fitness is just the number of digits that are set to 1 divided by the total length of the vector. So if I have 5 digits here or here, okay, same fitness at the end, different candidate solution, okay? And this is the one that's the worst, all zeros. This is the one that's the best. So it's another problem, okay? The knapsack problem, I used it as an example because it's a well-known computer science theoretical problem, okay? And it has a lot of industry application. Now we're switching to something simpler, the 1 max. That's what we are going to try to optimize. just to make sure our algorithm works. And once it works, we can apply it to more complex problems. The second part of the puzzle is the evolutionary algorithm itself. So now we have a problem to solve. Here is the algorithm I want you to implement to solve that one max problem. But potentially, if we change the fitness function, we can solve all sorts of problems. So evolutionary algorithms, as the name implies, are based on the evolutionary metaphor. We stole some ideas from biologists. We completely simplified them to the point that biologists are ashamed to even know us. And now we run with it and we say, hey, we can solve engineering problems with that algorithm, right? And then we realize also, hey, we don't even understand how this algorithm works. That's why we still do research on it. So the idea is you have a population of individuals. So an individual is going to be a candidate solution, okay? What we are even more interested in is the genetic material of the individual. So we abstract, right? So that chain, that vector of bits is kind of like the DNA of a candidate solution. Okay, that's where the metaphor connects the dot. And this is what we want to evolve. We want to evolve the DNA of those candidate solutions, just like nature evolves, DNA of actually critters. Rest of the evolutionary metaphor, well, we have this population. It has an environment. Several different various types of nasty things happen in the environment. So you want to find actually the fitness of an individual, right? You want to measure how fit the individual is to a given environment. Well, in our case, our candidate solution, right, our binary string, we have this objective fitness quality function that tells us magically how fit they are for an environment. That's how, again, the metaphor connect. And pretty much what we're trying to do is we're trying to implement that survival of the fittest, principle from neo-Darwinian theories of natural evolution to solve optimization problems, okay? Quick parenthesis, survival of the fittest. So let me dispel a common misconception. Yes, we are using evolutionary principle to optimize, okay? But evolutionary principles are not meant to optimize. Many people think that survival of the fittest means you have to be the best. You have to be the fastest predator. You have to be the fastest prey to evade, the predator. You have to be the strongest, etc. Not really. This actually happened. Check it out. But no, being fit to an environment, that doesn't mean that you are the best. That means that you are viable, okay? That you're capable to survive in your environment. This is one example of a viable solution to a problem. That has nothing to do with the guy being the fastest, okay? So just make sure that even though we use evolutionary theory for optimization in this context, you don't overgeneralize, what I'm trying to say. An alternative interpretation of this kind of distinction is to survive the zombie apocalypse, you don't have to be the fastest runner. You just have to be having one person that runs less fast than you, okay? And you let the zombie catch up with him or her. Okay, so here's our metaphor. We have the fitness, we have the genetic material. So we have what is called the fitness landscape, which is our function we're trying to optimize. And we're looking for the best solution. Here's the algorithm. Very simple. At the beginning, I say I'm going to have a population. So there is this jargon, right, that we borrowed from biologists. I'm going to have this population of, let's say, 50 random, completely random individuals. So 50 random candidate solutions. And the first thing I do, I take each of those candidate solutions and I evaluate them with the fitness function. So for each candidate solution, I compute the fitness function, so 50 of them. So assuming I have 10 billion possible solutions, evaluating 50 of them is acceptable, okay? That's my first population. Then I'm going to apply a step called selection. So the purpose of selection is that I want in my population of candidate solution the best fit one to proliferate, to multiply. I want to have multiple copies of them. Okay, so if you have like 3 candidate solution with fitness is 1, 3, and 2, assuming you're trying to maximize the fitness in that example, okay, the candidate solution that has a fitness of 3 should find itself appearing in multiple copies in the next generation, in the next iteration of my algorithm. So selection is what makes good things appear more often in the population. Crossover, also known as recombination, is a way for us to take two different candidate solutions, mix and match their genetic material, their binary vectors, okay, one way or the other, and try to find randomly a better or worse solution. The worse are going to disappear due to selection, the better are going to proliferate. And mutation is even wilder than that. It's just take a candidate solution, so a binary vector, flip some of the bits, and there you go, you have a new solution. Is it better or worse? I don't care. Selection will take care of eliminating the bad ones and making the good one proliferate, okay? So it's not random search. Very important confusion. We do a lot of things randomly, but we have the selection pressure that guides us in the right direction. So in terms of binary vector, here's the first crossover we are going to implement. You take two candidate solutions with their binary string, you decide randomly where you want to cut the string, and you swap them around. That's it. That's called one-point crossover. That's the first one we're going to implement. Mutation, just for each bit in the vector, with a certain probability, flip it. So maybe all the 3 bits in black didn't get flipped, the one in red got flipped. That's it, as simple as that, okay? What is the outcome of this? I'm going to skip a little, well, this one I'm not going to skip, I'm going to skip the next two. This one is important. The outcome of this is that after a maximum number of iterations, we call them generations, I'm going to stop the algorithm, look at the population, pick the highest fitness solution, and I'm going to say, given the time you gave me to explore this problem, this is the best solution I can find. Good luck, right? So it's not guaranteed that I found the globally best solution in the entire search space. These methods are not giving you that guarantee. But on average, it's going to be a good solution, okay? So I'm going to skip this because really this is just a side remark, not really important. This is the one side I want to finish with. This is a pseudocode for a basic EA. So the graph, gave you an idea of what an EA look like. This is what I want you to implement, okay? So initialize the population P. So you have a parameter pop size, okay? That's the number of elements in a population, the number of candidate solution. And then you compute the fitness for each element of your initial population P. And then for 1 to max generation is going to be another parameter. Select 2 parents, we call them parents, 2 individuals from the population for breeding, P1, P2. Then apply crossover to P1, P2, you get offsprings, O1, O2. Then apply mutation to O1, and separately apply mutation to O2. So you see how we have like functions, methods that kind of sketch out here. And then compute fitness for O1 and O2 once you're done, with the crossover and the mutation. And then select for replacement. Find a slot in the current population and override the current individual there with your new offspring O1. And then do the same for O2. So we re-inject O1 and O2 in the population, okay? So some more detail about select for breeding. Select for breeding, we are going to use a method called K-tournament, okay? K equal 2 means I pick 2 individuals in the population. I look at their fitness. Which one is the best? That's the one I select, okay? So very easy. Select for replacement is going to be even easier. I have an offspring, I try to inject it into the population. I look through the population, which one is the worst individual right now? That one, I replace it. That's it, okay? And then crossover and mutation, when I went over the binary vectors, I pretty much covered that, okay? So no problem. We're going to stop here because we're getting kicked out of the room. One thing, take a look at the rest of the slide on your own. What's going to come next is an example of a run, okay? Like step by step what's happening. So that should be okay. And the last section is just suggestion on how to get started with the design, but that is something that we can also discuss during office hour, and you can discuss it with the TA during online session, and you can discuss it with one another on the forum. So let's use that, to clarify anything that needs to be clarified. Okay, but the main issue is generally with the definition of the algorithm. Yeah, you had a question?